Okay, welcome back. This is part three, the last part of covalent bonding. So I think it should be almost, yeah, that should be almost the last lecture for, in fact, the last lecture for most of us. Not for 104. Chem 104, you guys still have kind of one more, but this is the last for them. So let's just go into it. So notice that it didn't take you a while. It's just from 2, you're in 3. So you can tell that it was short on the same day. So let's just go into this multiple bonds. I keep it short so that you can be able to follow and not be bored by the long video. So multiple bonds, as the name implies, means that you can have normally you have one bond. Multiple mean that you have another, or you can have another on top of this order, which can be 3 bonds, or 2 or 3. That's multiple. So for molecular geometry purposes, multiple bonds have the same as single bonds. They have the same situation as single bond. So electron pairs are located in the same place between the nuclei, and the geometry of the molecule is determined by the number of terminal atoms, and not affected by the presence of double or triple bonds. So all these multiple bonds and the shapes, we try to keep it down because it can make it more complicated. Hence, the idea is just allow the multiple bonds slide. Oh no, I did this. Okay, let's just. That was a mistake, by the way. So the molecular geometries of the expanded octet, as if you can see, I think you see better with the slide. So now you're dealing with much more complicated or bigger size. I don't think we'll focus on this. I'll just skip past this because I can barely see the shapes, but just notice that you're now dealing with complicated shapes and complex structures, but they're very much good that you understand them. But for the sake of this lecture, I think you just forfeit these shapes because it's expanded octet, so it's more complex shapes. You can see that the previous one I told us of xenon fluoride, where you have a spindle-like shape where the lone pair creates a situation where the other molecules cannot move above or beneath, so just like that. So remember we did we did some of this previous. I think it's so hypochlorate, where you have the CO minus. So you see the shapes of this now get a lot interesting as well. So this is going to be I'm trying to find. Okay. So the first is a trigonal pyramid, and it's just a trigonal pyramid. Then the second now is trigonal planar because it doesn't have lone pairs. The first has a lone pair, so hence you have the pyramid situation. And then you have N2O, which is just linear. The reason why is because you have your terminals, and you have the terminal now is the central atom is oxygen, which has 6, and then nitrogen is the central and nitrogen is the terminal, which makes it interesting. It's the central and it's the terminal, hence you have a linear shape in this case, where it's going to be X O. Does that make sense? So it's O and 2 x's, hence it's straight linear. I think there's a mistake on this. Let me change it. Can I? Yeah. So the central is O, and then X is there. So you have that. Okay, it's correct. You have N as a central and N as also an attachment, so it's both. So you have that, so it's very correct. So because you have the central and the attachment, it's like this. Let me try to draw it down here so that you can see. So you have N attached to an N, and then attached to an O. So notice that N is the central and N is an attachment. So N is the central and N is an attachment. So hence you have a straight line, a linear shape, because the central and attachment kind of the same. So the whole lone pair, there's no lone pair around it. So straightforward. So that's that. Okay. There's what we call polarity, and polarity comes from the word polar, and polar means that you have poles, and when you have different poles, that's polar. Once you have the same, it's non-polar. So polar bonds are asymmetric distribution of electrons, and asymmetric means it's not symmetrical, it's not the same. Symmetry is the same. When somebody is symmetrical, my right and my left is symmetrical. When I have a situation where there's no symmetry, you see me walking in a different way, and the XX there can also be gender for ladies, and then XY is for men, means that the men are the ones that tell the gender. We have this thing in Africa where they assume that it's the woman that tells the gender. There are people looking for a male child and marrying a wife and finding out that they can't have a male child. I just put that in there. Well, it has nothing to do with the polar bonds. But the idea of polarity is just symmetry, where asymmetry, not symmetry. So polarity of a bond increases with increasing difference in electronegativity between two atoms. So when there's an increase in electronegativity, you have that push and pull because of asymmetric distribution of electrons. So you have one tending towards the other side and the other one pursuing or tending back. So you have that asymmetry, and that is what polarity is. That's what causes that tension and polarity. So we call them, the one end is the sigma, positive sigma, and then the other is a negative. So molecules may also possess polarity, that's positive and negative poles, and molecules are called dipoles. So dipole means you have two poles, so the poles there now can be positive and negative. So your hydrogen fluoride, hydrogen is a positive and tends towards a negative, which is fluorine, which is electronegative. So you have also the situation of beryllium difluoride, and in this case you can have it polar when it's beryllium fluoride, and then you have it non-polar when it's beryllium difluoride. And the question is why? What is that idea of the asymmetric situation? The moment there is no balance and symmetry, you have that charge, movement of charges, hence it's polar. But once it's symmetric, it's not polar. That very much explains the idea. Yeah. Okay. Yeah, think about it like this. When you carry a heavy bag on your right hand, Notice that your walk is going to be like this. You're going to be moving down like this towards one direction. But the moment you carry two heavy bags, notice that you're going to be walking normal. So there's no need for you to be moving differently. Very brilliant explanation for polarity. So asymmetric distribution of electron makes the electron wobble, in other words creating energy or transfer of electrons in the form of energy in a sense. But once it's symmetric, you have, and it explains this whole idea of what dissolves in water and what doesn't dissolve in water, what is soluble and what is not soluble, in other words, so what is miscible and what is not miscible. I don't want to go ahead of myself, but let me just continue. So you have the situation that we talked about here, where you have this beryllium difluoride. This is non-polar because notice this goes here, this goes there, symmetry. Then notice that in this case, remember how water is structured. This is going here, this is going here, and you have that asymmetric situation. Hence, water is polar on the strength of this whole activity of this one going here. Then you know this is going all out on the surface, like to and then it's balanced. But notice that this is all coming back in, so it's not really balanced. You just find it moving in and out. And then you have this one, not even, this is non-polar because all of this is going out. Notice that they're all going out, hence it's not polar. Then this is polar. This is polar because notice this comes in and this goes out. Yes, and there's varying polarity because this is 0 and this can have a good amount. This will have more, this will have less polarity. So notice they can be varying strength. So depending on the molecules and the electronegativity of the molecules involved in it. So determine which of the following is polar: SO2, CO2, or CH-Cl3. So guess, let's give a wild guess which of them is polar. Just guess. Pick one, you just have to pick one. Which of them? Okay. So if you notice, we're still using our A, X, and E. So A, X, and E is the terminal. You have to first look at the terminal atom identical. If yes, possibly non-polar. If no, possibly polar. So if the terminal, if they are both identical, then there's a possibility it can be non. And the reason for the identical, why it's going to be non-polar, is because what I told you. If you are carrying a heavy bucket of water on this hand and you carry another heavy bucket of water on this hand, that's going to result in some form of balance, and hence you have symmetry. But once it's not the same, it's going to be non-polar, and that is asymmetry. So that's, and then they said if A and X is asymmetry, etc. Okay, no. Okay, let's go into it. So we have A, X, 2, and E for the first, which is bent. And is the terminal atom identical? Yes. So it's okay. On the strength of the fact that it has an E, which is lone pair, so it's bent, and because of the bent nature, you'll have a situation where even the identical can result in a polar. The identical polar atom can result in a polar because there's an E now that shifts symmetry towards the direction because of the double bond. So you have, and then is it symmetric? No, polar in this case. Not all cases, but because of the presence of the lone pair. Then we have the next one, which is now plain, where you have this linear, it's not bent, it's linear, and then it has identical terminals, yes, which makes it non-polar. It has also symmetry, which makes it also non-polar. And then we have this other, okay, here we have the trichloromethane. It's called trichloromethane, so it's 3 chlorine and then methane, so it's called trichloromethane. So you have the AX4, which is tetrahedral, which is obvious. They're not going to be non-polar because of the awkward positioning of the attachments around in 4 places, so there's no any push and pull situation going on. So at the end of the day, we discover that what's polar is SO2. This is not. So if you chose SO2, which S is for Superman or Superwoman, you did it. So let's go down to atomic orbitals and hybridization. This is also another topic that you shouldn't really kill yourself about. You might not necessarily see questions from it. Hybridization. So remember, atomic orbitals, we did it previously. Look at any questions that has that because you can't escape it. So remember Pauling's principle. The full name is Linus Pauling. Is the one that gave us the famous Pauli principle with the orbitals, called Pauli. Was Pauling. So he's a Nobel Prize laureate. He's a Nobel laureate. That's in the year 1954. Some of you were not even born by then, including myself. So orbital diagrams, we know orbital diagrams, what they look like. You have a fluorine, and then the fluorine, you have the 1s, which has 2 electrons, and then you have the 2s, which has 2 electrons, and then you have the last, because fluorine has how many electrons? Remember, it has 9 electrons, but 2 inside and 7 outside. So you have 1, 2, 3, 4, 5, 6, 7. So it's 1, 2, 3, 4, 5, 6, 7. So you have 7. So notice it's going to be 1, 2, 3, and 4, 5. So in this situation, you will now have 1 hydrogen attaching to this, and then you have the whole balancing situation happening. And by the way, notice this hydrogen comes in and fills in that space. So remember, it's an orbital diagram we're looking at, so you don't get yourself confused. We're just trying to show us how the interaction happens between hydrogen and fluorine to make up what we have here. So the valency bond theory is quite interesting, and it can get you worked up on what is going on, and sometimes it can be, but just understand that there are some limitations to it, and we'll see the limitations to it. So unpaired electrons from one atom pair with unpaired electrons from another atom to give rise to chemical compounds. We know that electrons interact with electrons and then they form new compounds, and that's what chemistry is basically about. The simple extension of orbital diagrams is just an extension of orbital diagram where you can mix them up and explain what just happened. But there are limitations to valency bond models, because the molecules that are formed from the electron deficient central atoms, such as the beryllium and the boron, are not explained by the valency bond model. So those complications cannot be explained, hence it doesn't hold water, hence it might not be sustainable. Because yes, you probably did not study and then you got 100 in your quiz doesn't mean that you consistently get 100 in other quizzes as well. That's a wrong example, but I think somebody might make sense of it, because that might just be you're lucky. So how then do you, so some discrepancies cannot be explained, and hence the model needs to be modified. So there's some certain, it works for this person but it cannot work for this person, and you can't explain why it cannot work for this person. So hence the whole idea now has to be looked on again, or other ideas that are consistent can be used to explain it. So you have the formation of XP hybrid orbitals. Now we're going to the realm of hybridization. Let me explain what hybridization is. Hybridization is simply the formation of a new from two distinct orbitals, where you have s orbital and p orbital comes together to form a hybrid. Some of you are familiar with this movies where you have a vampire and you have a werewolf, and then you see the movie's storyline is going to go like this: the werewolf falls in love with a vampire, and then the vampire and the werewolf got married and they give birth to a hybrid, which is a mixture of the werewolf and the vampire. And then the hybrid will have the properties of the werewolf and the properties of the vampire. That's just the same idea. So you have hybrid cars. Hybrid cars are cars that use both batteries and electricity to work. So that's just the idea. The idea is just bringing two different worlds together to form one unique wall or unique stuff. So the s orbital, remember, is 2 electrons, and the p orbital is 6, which is 3 compartments. Hence, when the two come together, you have that hybrid situation, and that's what we explain in hybridization. So, and notice with the hybridization, you have some new properties because it's mixing the two together. So when you have one s and one p, you now have 2 s and p. So 1s, 1p, you have an s and a p, and an s and a p again. So you have these two because of the two forming together. So you have a mix. So it's like, I hope that makes sense to somebody. So you can have a situation where you have number of electrons, and then the orbitals, and then the hybrid orbitals that can be formed as a result of that. And we're trying to compare how this hybrid explains the shapes and orientations that we saw previously, still tied into geometry. All of these different things, Lewis structure, all of it, we're just trying to explain out the shapes, and it will make a whole lot of things make sense if you just understand it. So the SP hybridization can give you an S and a P, which is linear, and the explanation is this: because once you have one S and one P, it gives you 2 S and P, right? And that 2 S and P will just lift them on the linear plane. Then when you have 1 S and 2 P's, notice that with 1 S and 2 P's, you're going to have 3, and that 3 will give you the trigonal planar. And then the 1S and 3 P's, remember, we're not adding S's because S just has 1, but the other ones can have several. So the 3 P now will give you a tetrahedron because you have a total of 4. So just be adding them. S and P, 2. 1 S and 2 P's, 3. That's why you have tetrahedron. Then 1 S and 3 P's, you have tetrahedron, which is 4. Then 1 S, 3 P's, and 1 D is a trigonal bipyramidal. And notice that the D there will mean that you have a compound, you have an element that is a transition metal. Hence, you see the complication comes with the more electrons that you have. I hope somebody make sense. Then 2Ds will mean, because note that it's the suborbitals that is counting. 2Ds, you can have 3Ds, it goes on like that. So the hybrid orbitals and electron occupancy. So some rules observed before. In an atom you have orbitals that holds 2 electrons. You have in a molecule you have orbitals that holds 2 electrons. So electrons in hybrid orbitals, you have lone pairs, you have 1 pair per bond, right? You have 1 pair per the bond, you have lone pairs and then 1 pair per bond situation. Even for double bonds, only 1 pair goes into the hybrid. So double bonds, it's just 1 pair of electron that goes into the hybrid. So the hybridization of nitrogen, nitrogen, ammonia, and this, we're going to see those states in this example question. Is state hybridization. Okay, for this, okay, let's just look at it. So in this case, notice that you have N, which is the central, and 3, and then the E. So if you look at it very closely, the N has how many electrons on the outermost shell? It has 5. 2 are the lone pairs, 3 are the bonding pairs, right? And then on the strength of that, you have your M, which is 3, and then your 1, which is the lone pair. And if you add all of those together, you have your sp3, which explains the trigonal pyramid that you see in ammonia. Because if you remember, sp3 is a tetrahedron. No, in this case, a trigonal planar. A tetrahedron, sorry. Yeah, tetrahedron, sorry. Because the tetrahedron is that one attachment above. That one attachment above. That one lone pair that we see above. So that's the sp3 situation. And then we have for the other ion, where you have an sp2, and this sp2 is just your situation enemy. So notice the whole concept is the nitrogen has first the s2 electrons on the s and then 3 on the p. So on the strength of the hybridization, because the 2 is up and then the 3 is at the side, and then because of this 3, it pushes, you have the hydrogen coming on 1. I'm trying to make it so you have 2 electrons, which are the s, and then the 3 electrons, we are the p. So the hybridization will now make them like this, and then the other hydrogens will fill in this place, and then you have the sp3, which is 1s and 3 p's, p orbitals together to form that hybrid. And then the nitrogen dioxide will be same situation. You have the orbitals of oxygen, and then the orbitals and 2 of the p, that's s, and then 2 of the p coming to form, give you 3, and on the strength of that 3 you have that form of hybridization, sp3 hybridization. You have the 2, and then you have the 1, which is the lone pair, and then you have the nitrogen gas, which is triple bond, and then the 2 at the side, which is obvious. We have 1 and 1, which is your sp. So that the bonds, where you see the bonds, most especially when you see the double bond, is very indicative of sp2. When you see the single bonds, very indicative of sp3. When you see the s and the p, is very indicative of the triple bonds. So we'll see that very evidently with carbon. So there's what we call sigma bonds, and the sigma bonds are like the main bonds around, and the pi bonds are the overlapping bonds. simple put. So the sigma bonds, electron density is located between the nuclei, as we saw in the beginning where we showed us the cloud density nuclei, and then the one pair is equal to, so a one pair of a bond, just a bond which is a pair of electrons, is the sigma bond. That's the normal bonding that we see around. Then the electron density located above or below or in front or at the back of the nuclei. So this one is almost like in front, behind, above or below is the pi bond, and it's mostly what forms a double bond. So when you have one pi bond, it's a double bond. When you have two pi bonds, it's a triple bond. So this is what it looks like when you have a pi and a pi. This is indicative of a double bond. A pi and a pi, pi and pi is triple bond. So this is ethylene, acetylene. So the sigma is the normal highway, so like the normal road. Then this is the road at the side of the normal road, which makes it double. Then this triple here and here. Hence the whole idea of your SP. So the SP will mean that you have everything all in alignment, while the SP2 will mean that you have just two, one alignment. So three in alignment, two in alignment. Three will mean that you have everything spread. Then 2 will mean that you have the 2. Then SP will mean that everything will align to form a triple bond. So we have they said give the number of pi and sigma bond in Na3, NO2 minus, and N2. So you can do this because this is the same things you got from the last. So what's the number of pi bonds? Because Na3 is sp3, so do the math. I just give you the answer unknowingly, so you can find the rest. So let's just go into it. We're almost done. So the Lewis structure for the species given, sorry, you have the MP. So already you have 3 sigma bonds, and then you have no pi bond. There's no pi bond. 3 sigma bonds, no pi bond for the first. Then you have NO2, and NO2 will mean that you have 2 sigma normal, and then do you have a pi bond? Yes, you have 1 pi bond. And then the N2 will mean that you have 1 sigma and 2 pi's, and that's how it goes. So you have 1 sigma, and then because of the 3 minus 1, you have 2, which you have 2 pi. So I said earlier, because it has triple bond, the normal bond is the sigma, and then the overlapping bonds are the pi. So the other one, the other case, and you use the M and the N to work that through, because the bonds minus M is your pi bond, while the M itself is your sigma bond. So that's out of the way. You have your M here. Yeah. So I hope. So at the end of the lecture, we're able to draw Lewis structures for molecules and also diatomic ions, because we saw hydroxide ion, different ions, ammonium ions. We're able to draw the Lewis structure, and we saw what resonances are, and also write and draw resonance structures as well. Then we looked at the valency share electron pair repulsion theory, and able to predict some molecular geometries, and then saw polar and then non-polar, looked at hybridization, and lastly talked about the sigma and pi bond species. So that's it. So we're done with this lecture, and that's the end of the covalent bonding. If you have any questions, you can send an email, but I think those of you that will see in the face-to-face, you're free to ask your questions. But those of you online, you can send an email, or we can do a concluding class at some point in time that will fix, and then we can do that together for all the questions with regards to the topics that we've discussed. So that's it. And do have a happy new year, because I think some of you will be watching this either get into the new year or at the end of the new year. So take care of yourselves and do have a lovely new year.